Hi everyone, let's look at a little bit of probability and randomness. So here we have a screenshot from a game where this player here is in some sort of computer simulation and wants to attack this enemy that's trying to stop her from accessing the elevator override. So the number to look at here is 67%. This character has a 67% chance to hit this enemy with some sort of digital attack. So what does that really mean though? Well, when things are given as a probability like this in a game, it usually means that if you were to repeat this over and over again with random numbers, 67% of your attempts would actually hit the enemy and the other 33% would not. So what does repeated attempts, though, look like? How many trials do you need to make that a reality? So we can do a simulation in Excel, which I have here. I've set up 3 different random situations. Here we have 10 trials. And you can see the Excel commands I'm using, rand between 1 and 100, just to generate a random number between 1 and 100. And then here I have this formula I don't think we've talked about, but it uses the. So if this is less than 33, less than or equal to 33, it's a miss. Otherwise, it's a hit. And here we do it 10 times. Here we do it 500 times if you scroll all the way down. And here 10,000 times just to see what the result was. Put the results over here. For n equals 10, with these random numbers, we hit 4 times and missed 6. So that's only a 40% hit rate, which is very, very different than that 67% that we were supposed to. And then here I put, some expected calculations like, if 67% of the time you hit and you try 10 times, then you expect to hit 6.7 times. And of course, that's a decimal number, but those are fine in math in a lot of situations. You can't really hit 6.7 times out of 10 trials, but for the math, it's fine to use decimals. And similarly, you'd expect to get 3.3 misses. So the random numbers updated here as I looked at the formula, and you can see now we have 7 hits, 3 misses, which is 70%, which is much, much closer to the 67%. You look at the same thing as we go into more trials. With 500 trials, we were almost right on the money here, 66.6%. If we generate new random numbers, you can see the n equals 10 result. We'll jump around a little bit. This is way off, but it could be much higher. I got 80%. It could be, I've seen even 90 or 100% while I was playing around with this, though 100% is a little less likely. But the n equals 500, it doesn't change nearly as wildly. This is low, 63.6, and some other times it might be a little high, 69.6, a bit higher than 67. But closer, it's really only off by a couple percent. And, if we did n equals 500 like over and over and over again, we'd get an idea of how spread out these numbers could be. And of course, spread out numbers, we might then talk about standard deviation. That's a little further down the road, though. So then we look at the n equals 10,000 trials. And here, with these random numbers, we have 66,703 hits, which is very, very close to our 67% theoretical. And then when we keep updating, we notice these numbers are pretty much always very close to 67%. It might be 67.27, 66.81, something like that, but it's always very close. And you see here we have the difference between expected and observed. And even if that's like we're off by 17 total difference from expected, it's still that 67.17%. The percentage is very much the same. And this is what we mean by the law of large numbers. As with more and more observations, more data, more trials, whatever you call it, the observed relative frequency, so this number, will become closer to the theoretical frequency, or often called probability. So if we went not equals n equals 10,000, but 20,000, 100,000, whatever, Excel could do that, though it will slow down a little at some point. It would be even closer and closer to 67% on each try. Of course, in that video game we were just looking at, I've actually collected data when I first bought it, and the game it's not accurate about its probabilities. Like I tracked data for like a couple hundred different hits, and it just did not match at all closely enough for me to feel like the numbers it was giving me were realistic. And that's something that you can do, if you do enough statistics, you can either do like formal tests of like, we talked about hypotheses in week 1, like the game's probabilities are accurate as stated or they're not, and we can test the hypothesis. which is something we might do a little bit later, but we'll see how technical we want to get. Anyway, hopefully that gives you an idea of probability. When you use small sample sizes, you can get really strange things can happen. Like you have a 67% chance to hit, but in this simulation, you missed 4 times in a row. That's unlikely, but it can happen. Then you miss 3 times in a row again. Whereas, here, 1, 2, 3, 4, 5, 6 hits in a row. So when you're talking about randomness, there really is quite a lot of variability that can occur. And so just be aware that small sample sizes have a lot of variability.